Our history was written in the stars long before we walked the Earth. From the violent birth of our moon to stellar explosions that forged the elements of life itself, the cosmos has repeatedly intervened in our story. By the end of this journey, you will discover the 25 cosmic events that fundamentally shaped human destiny, from our deepest past to our ultimate future. We will explore how a single day of solar fury nearly ended the modern world, and why an interstellar visitor may hold secrets to our own origins. What invisible force from the depths of space do you think is quietly shaping our lives right now? 4.5 billion years ago, our world was a very different place. The young Earth was a seething ocean of molten rock, a hellscape under constant bombardment from the leftover debris of the solar system's formation. It was in this chaos that our planet's single most defining moment occurred. A rogue planet roughly the size of Mars and now known as Theia was drifting on a collision course. This was not a mere glancing blow. Theia struck the early Earth with a cataclysmic force that is almost impossible to comprehend, hitting with such energy that it nearly vaporized both worlds. The entire globe turned into a spinning, incandescent cloud of vaporized rock and metal. From this unimaginable violence, our future was forged. A significant portion of Earth's mantle was blasted into space, mingling with the shattered remains of Theia. This debris field, a glowing ring of destruction, began to orbit the young planet. Gravity quickly took over, pulling the fragments together in a process of cosmic accretion. Within just a few thousand years, this ring of fire coalesced into the beautiful, serene moon we see today. But the moon's creation was more than just a celestial ornament. It was the gift that made our world livable. The impact set Earth spinning at just the right speed and, most crucially, stabilized our planet's axial tilt. Think of a spinning top. Without the moon's gravitational influence, Earth would wobble wildly on its axis over millions of years. This chaotic wobble would cause our climate to swing violently between extremes, making the stable, predictable seasons we rely upon for agriculture impossible. The steady rhythm of spring, summer, autumn, and winter is a direct consequence of that ancient crash. This stability provided the consistent environmental conditions necessary for the first single-celled life to not only emerge but to thrive and evolve over billions of years. Our entire biological clock, the very tempo of life on Earth, was set in motion by a single, shattering blow from the cosmos. That stable, life-friendly Earth was not yet safe. The calm after the moon's formation was brutally interrupted by a second, prolonged cosmic assault. For hundreds of millions of years, beginning around 4 billion years ago, the inner solar system became a shooting gallery. Asteroids and comets rained down upon our planet and its neighbors in an event scientists call the Late Heavy Bombardment. The scars of this violent era are still visible on the face of our moon, a silent testament to a time when Earth was constantly pummeled by celestial projectiles. It seemed like a period of pure destruction, a force that would sterilize a young world. But this chaos was in fact a creative force. These asteroids and comets were not just barren rocks and balls of ice. They were cosmic delivery trucks carrying precious cargo from the far reaches of the solar system. With every fiery impact, they released vast quantities of water, vaporizing on contact and eventually cooling to form the first true oceans. The very water that fills our seas and flows in our veins was a gift from this ancient bombardment, but the delivery did not stop there. Locked within these space rocks were complex carbon-based molecules, the fundamental organic building blocks of life itself. Amino acids, the components of proteins and nucleobases, the letters of our genetic code, were all raining down from the heavens. This constant influx of raw materials into the warm, shallow pools of the early Earth created a rich primordial soup. In this nutrient-rich environment, subjected to the energy of lightning and volcanic heat, these non-living ingredients began to assemble, to react, and to complexify. The relentless cosmic pounding that seemed so hostile may have provided the final, crucial push, supplying the exact ingredients and conditions needed for the first self-replicating molecules to emerge from the chemistry of the planet. The violence of space, once again, was the unlikely midwife to life. These life-giving impacts were just the beginning of a much larger cosmic story. The very atoms that make up our solar system were forged in the heart of ancient, dying stars. Before our sun even ignited, a colossal supernova erupted somewhere in our galactic neighborhood. The shock wave from this stellar explosion, traveling at millions of miles per hour, slammed into a vast, quiet cloud of gas and dust. It was this cosmic pressure wave that compressed the cloud, triggering its gravitational collapse. From that initial push, our solar system began to spin into existence, with the sun forming at the center and the leftover material coalescing into the planets. We are quite literally the children of a star that died long ago, but the cosmic influence did not stop with our creation. As life on Earth was taking its first tentative steps, the sun was younger and significantly dimmer. The planet should have been a frozen ball of ice, yet geological evidence shows it was warm and had liquid water. This is known as the faint young sun paradox. One compelling theory suggests a solution written in the stars. A slightly higher flux of cosmic radiation, perhaps from a nearby supernova or our own active young sun, could have provided the extra energy that kept the early Earth warm. This same radiation may have also played a role in mutating and driving the evolution of the first simple life forms. Among these were the cyanobacteria, humble organisms that discovered how to harness sunlight for energy through photosynthesis. Their waste product was a gas that was poison to most other life at the time, oxygen. For 2 billion years, these tiny organisms slowly but relentlessly pumped oxygen into the atmosphere, transforming it completely in the Great Oxidation Event. This was the first and most profound planetary pollution crisis. The oxygen rusted the oceans, stripping iron from the water, and caused the extinction of vast swaths of ancient anaerobic life for whom oxygen was toxic. Yet this cataclysm paved the way for everything that followed. The oxygen eventually formed a protective ozone layer, shielding life from harmful solar radiation and allowing it to move onto land. More importantly, it enabled a much more efficient form of energy production within cells called aerobic respiration. This new power source provided the energy necessary for life to grow larger, more complex, and eventually evolve into the incredible diversity we see today, including us. A stellar death and a planetary poisoning, two cosmic events that cleared the stage for a new, more vibrant act in the story of life. The oxygen-rich world that cyanobacteria built was a stage waiting for its next great actors. For over 160 million years, those actors were the dinosaurs, ruling a lush and vibrant planet. Then, in a single day, their world ended. 66 million years ago, a mountain-sized asteroid over 6 miles wide was on a fatal collision course with Earth. It was not a slow, drifting rock. It was a bullet traveling at over 40,000 miles per hour, striking the shallow seas of what is now the Yucatan Peninsula in Mexico. The impact, known as the Chicxulub event, released more energy than billions of atomic bombs. The immediate effect was a firestorm that scorched the continent, but the real killer came from the sky. The impact vaporized trillions of tons of rock, hurling it into space, where it condensed into billions of tiny, glassy beads. These superheated beads rained back down through the atmosphere, heating the air until it became a global oven, igniting forests worldwide. Then, as the dust and soot blotted out the sun, the planet plunged into a long, dark winter. Photosynthesis stopped, the food chains on land and in the sea collapsed. With the dinosaurs gone, a new world order emerged from the shadows. Small, scurrying mammals who had survived by living underground and eating seeds or insects found themselves on a planet with empty ecological niches. They were no longer prey. This cosmic catastrophe was the pivotal opportunity that allowed our own ancestors, tiny shrew-like creatures, to begin their own evolutionary journey, a path that would eventually lead to us. Much later, another global catastrophe would shape humanity itself. Roughly 74,000 years ago, a different kind of disaster erupted, this time from deep within the Earth. The Toba supervolcano, located in modern-day Indonesia, exploded in the largest volcanic event of the last 2 million years. It ejected so much ash and sulfur dioxide into the stratosphere that it created a volcanic winter lasting for years, possibly even decades. Global temperatures plummeted. The evidence is stark. Geological ice cores from Greenland and Antarctica show a sharp spike in sulfuric acid from this exact period. More tellingly, genetic studies of modern human populations point to a severe bottleneck around the same time. The global human population may have crashed to as few as 1,000 to 10,000 breeding pairs. We were pushed to the very brink of extinction. This was not a random event. Some scientists propose a fascinating cosmic link. They suggest that subtle gravitational tugs from other planets, influencing Earth's orbit and rotation, can increase stress on the planet's crust, potentially triggering such extreme volcanic activity. The Toba catastrophe may have been a terrestrial event with a celestial trigger. This near annihilation forged modern humanity in the crucible of disaster. With resources desperately scarce, only the most intelligent, cooperative, and adaptable groups survived. This immense evolutionary pressure may have accelerated the development of complex language, sophisticated social structures, and advanced tool use. The survivors of this bottleneck did not just endure, they eventually began a great migration out of Africa, repopulating the world with a new kind of human, one shaped by a star-crossed disaster. That near extinction forged a species uniquely attuned to the patterns of the world and the sky above. For our ancestors, the heavens were not a silent void but a canvas of meaning where gods and fate were written in the light of stars. One such celestial event, witnessed 2,000 years ago, would become perhaps the most famous star in human history. The Star of Bethlehem, as described in the Gospel of Matthew, was a sign in the heavens that heralded the birth of Jesus Christ and guided the Magi, the wise men from the east. For centuries, it was considered a pure miracle, a singular divine light. But modern astronomy asks a compelling question. Could a real, observable cosmic event have been the inspiration for this story? Several fascinating possibilities exist. One of the strongest candidates is a rare triple conjunction of the planets Jupiter and Saturn. In the year 7 BCE, these two bright planets would have appeared to pass extraordinarily close to each other not once, but 3 times over several months in the constellation Pisces. To ancient astrologers, this would have been profoundly significant. Jupiter was often seen as a kingly planet, while Saturn was a symbol of the Jews or protectors of Palestine. Their meeting in Pisces, a sign associated with the region of Israel, could easily have been interpreted by learned magi as the announcement of a great king's birth in Judea. Another possibility is a brilliant comet. Chinese astronomical records note the appearance of a bright comet in the year 5 BCE, which remained visible for more than 70 days. Comets, with their long, dramatic tails, have always been seen as celestial messengers and harbingers of change, a perfect sign for a new era. Or perhaps it was a nova, a star that suddenly flares to immense brightness before fading away. A new star appearing where none was before would certainly have been seen as a monumental omen. Regardless of its precise astronomical identity, the impact of this perceived celestial event is undeniable. It cemented the idea of a cosmic connection to a pivotal moment in Christianity, influencing 2 millennia of Western art, literature, and music. The star is depicted in countless paintings and mentioned in hymns sung by billions. More practically, the quest to pinpoint the year of Christ's birth based on this star led directly to the creation of the Anno Domini system by a monk named Dionysius Exiguus in the 6th century. This system, which counts years from the birth of Christ, forms the basis of our modern global calendar. A single interpreted light in the sky, whether a planetary meeting or a stellar explosion, helped structure the very way we measure time itself. It is a powerful testament to how humanity has always looked to the cosmos not just for physical laws, but for spiritual meaning, weaving our deepest stories into the fabric of the stars. That same human impulse to find meaning in the stars would face an undeniable cosmic spectacle nearly 1,000 years later. In July of 1054, as dawn broke over the city of Kaifeng, Chinese court astronomers witnessed something impossible. A new star, a guest star as they called it, blazed with terrifying brilliance in the constellation Taurus. It was not a faint twinkle. This star outshone every planet and every other star in the sky, so luminous it was visible in broad daylight for 23 consecutive days, and it remained a naked-eye object in the night sky for nearly 2 years. Meticulous records from the Song Dynasty court detail its position and changing colors, a stunningly accurate account of a stellar death. Across the sea, Japanese stargazers also noted the mysterious star, while on the other side of the world, ancestral Pueblones in the American Southwest may have captured the event in a petroglyph, a hand carving showing a crescent moon positioned right next to a large, distinct star, matching the known celestial arrangement from that time. Yet in Europe, the record is a profound and telling silence. Why would such a world-altering event go unmentioned in Western chronicles? The answer lies in the rigid cosmology of the medieval church, which held that the heavens beyond the moon were perfect, eternal, and unchanging. A new star was a theological impossibility, a direct challenge to dogma, so it was likely ignored or deliberately not recorded. This single event, therefore, created a historical map of human thought, separating cultures that observed the heavens with empirical curiosity from those bound by immutable doctrine. The star itself faded from view, its story preserved in silk and stone, becoming a celestial mystery for centuries. Then, in the 1700s, astronomers peering through telescopes noticed a faint, fuzzy patch of gas in that exact spot. They called it the Crab Nebula. We now know this cloud is the expanding wreckage of that very supernova, a cosmic crime scene we can still observe today. At its heart lies one of the most fascinating objects in the universe, the Crab Pulsar. This is the crushed, ultra-dense core of the exploded star, a neutron star spinning 30 times every second, sweeping the cosmos with lighthouse-like beams of radiation. The Crab Nebula became a living laboratory, the first object identified as the remnant of a historical supernova, confirming that stars do indeed die in catastrophic explosions. It proved that the heavy elements forged in these blasts are scattered into space, eventually to be incorporated into new stars, new planets, and ultimately new life. The event that medieval Europe refused to see became one of the most important touchstones of modern astronomy, a brilliant death that illuminated our understanding of cosmic life cycles. Just over 4 centuries after the Crab Nebula's light faded, the silent heavens spoke again with a voice of thunder. In November 1572, a new star, brighter than Venus, erupted in the constellation Cassiopeia. It stunned everyone who saw it, from common farmers to the most learned scholars of Europe. For the Danish nobleman and astronomer Tycho Brahe, it was a call to action. He turned his entire life toward understanding this celestial intruder, building the most advanced observatory of its age, Uraniborg, and dedicating himself to a campaign of measurement more precise than any that had come before. Night after night, he and his team tracked the star's position and its slow fade. The central question was simple yet earth-shattering. Was this new object a nearby atmospheric phenomenon like a comet, or was it truly a star located in the distant realm of the fixed stars beyond the moon? According to the 2,000-year-old doctrine of Aristotle, the heavens beyond the moon were perfect and unchangeable. A new star in that domain was a metaphysical impossibility. Yet Tycho's meticulous data revealed a profound truth. He detected no parallax, meaning the star did not shift its position relative to the background stars when viewed from different points in Earth's orbit. This proved beyond any doubt that the new star was immensely far away, residing in the supposedly immutable celestial sphere. The Aristotelian universe, the intellectual bedrock of Western civilization, had a crack running straight through its core. This single observation did not just add a new star to the sky, it shattered the ancient concept of a perfect, unchanging cosmos and opened a door to a new kind of science, one based on empirical evidence rather than pure philosophical dogma. Tycho's supernova was the catalyst that forced European astronomy to look forward, not backward. His precise data on planetary motions, later inherited by his assistant Johannes Kepler, would become the foundation for Kepler's laws of planetary motion, which in turn provided the crucial evidence for a sun-centered solar system. The death of a distant star, meticulously recorded by a man with a metal nose, helped kill the Earth-centered universe and set the stage for the scientific revolution, a fundamental shift in how humanity understood its place in the cosmos. The crack in the perfect celestial sphere was about to be torn wide open. Just 32 years after Tycho's supernova faded, the sky delivered a second, undeniable blow to the old worldview. In October 1604, a new star, now known as Kepler's supernova, blazed to life in the constellation Ophiuchus. It was brighter than Jupiter, a scintillating jewel visible to anyone who looked up. This time, the European intellectual climate had shifted enough for the event to be met not with silence, but with intense scientific scrutiny. The brilliant astronomer Johannes Kepler, who had inherited Tycho Brahe's treasure trove of planetary data, turned his full attention to this new marvel. He studied it for over a year, meticulously documenting its brilliance and its slow fade, just as his predecessor had done. His observations provided the final, conclusive proof that the heavens were not static. Stars could be born, live, and die in spectacular fashion. The cosmos was alive with change, but these stellar deaths were far more than just spectacular light shows. They were cosmic forges, and Kepler's supernova helped reveal their true purpose. Within the unimaginable pressure and heat of a supernova blast, a miraculous process occurs. The simple elements like hydrogen and helium, which have existed since the dawn of the universe, are fused together into heavier, more complex atoms. In that single, violent instant, a dying star manufactures carbon, oxygen, nitrogen, and iron, the very elements that form the bedrock of our planet and our bodies. All the iron in your blood that carries oxygen, the calcium in your bones that gives you structure, and the oxygen you breathe with every lungful of air were forged in the heart of a star that no longer exists. The cataclysm of a supernova is what scatters these newly created elements across space, seeding vast clouds of gas and dust with the ingredients for new solar systems. Our own sun, Earth, and everything on it are made from the recycled remains of these ancient stellar explosions. We are, in the most literal sense possible, made of stardust. Every time you look up at the night sky, you are looking at the distant relatives of the very stars that died so that you could live. The stardust that forged our world also holds the power to undo our civilization in a single, silent blast from the sun. On the morning of September 1st, 1859, the English astronomer Richard Carrington was observing sunspots through his telescope when he witnessed something unprecedented. Two patches of intensely bright white light erupted from the solar surface, vanishing just 5 minutes later. He had just documented a massive solar flare, a direct hit from our own star. Within hours, the effects reached Earth. The night sky, from the Caribbean to the Rocky Mountains, erupted in a curtain of blood-red, green, and purple auroras so brilliant that people could read newspapers by their light. Gold miners in the Rocky Mountains, confused by the shimmering colors, woke up and began making breakfast, convinced it was morning. But the true power of this solar storm was not in the sky, but in the wires. The telegraph was the internet of the 19th century, a global network of copper wires and Morse code. As the geomagnetic storm intensified, it induced massive electrical currents in those very wires. Telegraph systems across Europe and North America catastrophically failed. Operators received severe electric shocks from their equipment. Telegraph papers spontaneously caught fire. Pylons threw sparks, and the machines continued to tap out garbled messages even after being disconnected from their power sources. It was as if the sun itself had reached down and seized control of humanity's most advanced technology. The Carrington event was a terrifying and transformative moment. It proved that space weather was a real physical force, and that our planet was not an isolated island but a ship sailing through a cosmic sea of energy. The profound threat today is almost incalculable. A storm of the same magnitude would not just burn a few telegraph papers. It would send destructive currents through our vastly more complex and interconnected power grids, potentially causing widespread, long-lasting blackouts that could span continents. It would fry the delicate electronics in satellites, crippling global positioning, communications, and financial networks. It would be a silent, invisible hurricane that could collapse the infrastructure of modern life for months or even years. The Carrington event was a warning shot, a demonstration of solar power that arrived when our technology was still in its cradle. The next time the sun unleashes such fury, our world will be listening whether we are ready or not. The sun's silent fury was a stark reminder of our cosmic vulnerability, but it was a blast from the depths of the solar system that truly made humanity look up with fear. On the morning of June 30th, 1908, in a remote part of Siberia near the Podkamennaya Tunguska River, a fireball brighter than the sun tore across the sky. Moments later, the world exploded. The force of the blast was thousands of times more powerful than the atomic bomb dropped on Hiroshima. It flattened an estimated 80 million trees across 800 square miles of forest, radiating outward from the epicenter in a vast butterfly-shaped pattern of destruction. The seismic shockwave registered on barometers as far away as England. For nights afterward, skies across Europe and Asia glowed so brightly that people could read newspapers outdoors at midnight, the result of vast amounts of ice and dust thrown into the upper atmosphere. Yet for years, the cause remained one of the planet's greatest mysteries. Expeditions to the site were delayed by the region's extreme isolation and the political turmoil of the Russian Revolution. When scientists finally reached the epicenter in the late 1920s, they expected to find a giant crater and pieces of a meteorite. They found neither. There was only a zone of scorched, flattened trees, with a few still standing at the center, stripped completely bare of their branches. This absence of a crater was the crucial clue. The object, now believed to have been a stony asteroid or a fragile comet roughly 200 feet across, never actually struck the ground. It disintegrated in a massive airburst 3 to 6 miles above the Earth's surface. The resulting shockwave was like a titanic bomb detonating in mid-air, delivering the full force of a cosmic impact without leaving a single piece of itself behind. The Tunguska event was a cosmic wake-up call delivered directly to an empty theater. Had it occurred just 4 hours later, the rotation of the Earth would have placed a major European city directly in its path, resulting in the utter annihilation of millions of lives. This near miss fundamentally changed our perspective. It was the first undeniable proof that Earth exists in an active shooting gallery, and that a catastrophe of biblical proportions could arrive at any moment without warning. The event initiated serious, sustained scientific efforts to understand these threats. It sparked the modern field of near-Earth object tracking, pushing governments and space agencies to finally look up and map the paths of asteroids and comets that cross our orbit. The silent, empty sky over Siberia forced us to confront a simple, terrifying truth. Our civilization could be undone in an instant by a random piece of cosmic debris, and if we do not pay attention, the next one will not miss. The silent threat from the sky was not just the occasional asteroid. A constant, invisible rain of high-energy particles from deep space has been bombarding our planet for its entire history. In the early 20th century, scientists were puzzled by mysterious radiation that seemed to come from nowhere. They noticed that electroscopes, instruments used to detect electric charge, would slowly discharge even when perfectly shielded in lead containers. This suggested that some form of incredibly penetrating radiation was constantly passing through the Earth itself. The Austrian physicist Victor Hess decided to take his instruments to the sky. In a series of daring balloon flights, some reaching altitudes of over 3 miles, he made a crucial discovery. The radiation did not decrease with height. It actually became more intense. This proved the source was not from the ground or the sun, but from somewhere far beyond our atmosphere. Hess had discovered cosmic rays, and he would later receive the Nobel Prize for revealing that we are all living at the bottom of an invisible cosmic ocean. These are not rays of light, but rather a hail of subatomic bullets. Most are protons, the nuclei of hydrogen atoms, accelerated to nearly the speed of light by the most violent events in the universe, like supernova shockwaves and the jets of black holes. When these primary cosmic rays slam into the upper atmosphere, they shatter air molecules, creating a spectacular secondary shower of exotic particles that rains down upon us. This invisible downpour became humanity's first natural particle accelerator. Before we could build giant machines like the Large Hadron Collider, cosmic rays were the only way to study high-energy physics. In 1932, a cosmic ray interaction in a cloud chamber led to the discovery of the positron, the antimatter counterpart of the electron, confirming a stunning prediction of quantum theory. Later, the muon, a heavier, unstable cousin of the electron, was also found in this cosmic shower. These discoveries, forced upon us by the sky, fundamentally expanded our understanding of the building blocks of the universe. But this cosmic rain has a tangible effect on our modern world. Every time you fly on an airplane, you receive a slightly higher dose of radiation from these particles, a real, albeit small, health consideration for frequent flyers and airline crews. For astronauts in the relatively thin shield of the International Space Station or on a journey to the Moon or Mars, this exposure is a major design and safety challenge. Cosmic rays also cause silent, random glitches in our electronics, occasionally flipping a single digital bit in a computer's memory, which can lead to corrupted data or even system failures in satellites and sensitive equipment. From revealing the secrets of antimatter to quietly influencing our technology and biology, this relentless, invisible storm from the galaxy is a constant reminder that we are connected to the cosmos in the most fundamental ways imaginable. That invisible cosmic rain was a torrent of unanswered questions, a mystery that seemed to defy the very laws of physics as we knew them. For centuries, we believed we understood gravity thanks to Isaac Newton's equations. It was a simple, elegant force of attraction, but a quiet revolution was brewing in the mind of a single patent clerk, and it would take a total eclipse of the sun to prove it to the world. On May 29, 1919, the moon slid perfectly in front of the sun, turning day into an eerie, twilight night. For 6 precious minutes, the star's brilliant face was completely obscured, revealing its shimmering corona and, crucially, the background stars in the constellation Taurus. 2 teams of astronomers, led by Arthur Eddington, had traveled to opposite ends of the Earth to capture this moment, one to the island of Principe off the coast of Africa and the other to Sobral in Brazil. Their mission was not just to watch an eclipse, but to conduct a single, critical experiment that would test Albert Einstein's radical new theory of general relativity. Einstein had proposed that gravity is not a mysterious force, but a warp in the very fabric of space and time. A massive object like the sun, he said, would bend the space around it, causing the path of anything passing nearby, even light itself, to curve. This meant that the light from distant stars skimming close to the sun's edge would appear to be slightly out of position. The only time you can see stars right next to the sun, of course, is during a total solar eclipse. Eddington's teams took precise photographs of the star field around the blacked-out sun. Back in England, they compared these eclipse plates to reference photographs of the same star field taken at night when the sun was elsewhere in the sky. The difference was tiny, a deflection of starlight amounting to just 1.7 seconds of arc, a measurement equivalent to the width of a human hair seen from 10 feet away. But it was there, the stars had indeed shifted. The results announced that November sent shockwaves through the scientific community and made Einstein an international celebrity overnight. The headline in the London Times read, "Revolution in Science, New Theory of the Universe, Newtonian Ideas Overthrown." A cosmic alignment had been used as a universal laboratory, proving that space is not a static stage but a dynamic, malleable entity. This single observation did more than just validate a brilliant theory. It opened the door to our modern understanding of the cosmos, from the Big Bang to black holes. It revealed that the universe is far stranger and more wonderful than we had ever dared to dream, all because we learned to read its secrets in the bent light of a distant star. Just 20 years after Einstein's theory was confirmed, the heavens gained a new man-made star whose simple beep would rewrite human destiny. On October 4, 1957, a polished metal sphere no larger than a beach ball was flung into orbit by a Soviet R-7 rocket. It was called Sputnik 1, and for 92 days it circled the Earth every 96 minutes. Its faint but persistent radio signal, a steady beep, 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 heard by every radio operator and amateur enthusiast on the planet. This was not a natural phenomenon or a distant cosmic event. It was a human artifact, the first artificial satellite, and its beeping was a declaration of technological supremacy that sent a seismic shock through the Western world. The United States was caught completely off guard. The idea that a rival nation could possess the capability to launch an object into space, and by extension, to potentially launch nuclear weapons across continents, created a profound crisis of confidence. The sky itself, once a realm of pure science and wonder, had suddenly become a new high ground in the Cold War. This single, beeping metal ball triggered an immediate and massive response. The American government, fearing a technological gap, poured unprecedented funding into science and technology education. The National Defense Education Act was passed, aiming to produce a new generation of engineers, scientists, and mathematicians. Public interest in space exploded, and the National Aeronautics and Space Administration, NASA, was created just 1 year later to centralize and accelerate the American space effort. The space race had begun not as a peaceful exploration, but as a surrogate battlefield for two superpowers. The ambition to reach the moon became a national goal, driving innovation at a breakneck pace. The integrated circuit, the predecessor to every modern computer chip, was developed in part to meet the demanding weight and computational requirements of the Apollo guidance computer. Satellite technology, pioneered by Sputnik, would soon evolve to give us global communications, weather forecasting, and the global positioning system. A simple beep from the cosmos, a sound born of political competition, ultimately catalyzed the technological ecosystem that defines our modern world. It proved that a spark from the stars, even one we placed there ourselves, could ignite a fire of human potential that would reshape civilization. That beeping from Sputnik ignited a fire that would burn all the way to the moon. Just 12 years later, the world watched breathless as a fragile lunar module named Eagle descended toward an alien landscape. When Neil Armstrong's boot pressed into the lunar dust in July of 1969, it was more than an American achievement. It was a moment of transformation for all humanity. For the first time, a living being from our world stood on another celestial body. His words, "One small step for man, one giant leap for mankind," perfectly captured the dual nature of the event, a feat of individual courage that belonged to the entire human race. But the true impact of the Apollo program went far beyond those first historic footprints. Perhaps the most profound gift from the moon was a new perspective on our own home. As the Apollo 8 spacecraft swung around the far side of the moon in December of 1968, the crew witnessed something no human eyes had ever seen: Earth rising over the barren lunar horizon. The photograph they snapped, Earthrise, became one of the most influential images in history. There was our world, a vibrant, beautiful, and heartbreakingly fragile blue and white marble, suspended in the vast black emptiness of space. It had no borders, no divisions, only a thin, glowing atmosphere that seemed to be all that stood between us and the void. This single image became the emblem for the global environmental movement, giving a powerful, visceral symbol to the concept of Spaceship Earth. It fueled a new consciousness that our planet is a single, interconnected system, a precious oasis that we all share and must protect. While that iconic view shifted our collective mindset, the technology required to get there quietly revolutionized our daily lives. The Apollo guidance computer needed to be small, light, and incredibly reliable, a challenge that pushed engineers to pioneer the use of integrated circuits. These tiny chips, which packed multiple electronic components onto a single piece of silicon, were a radical departure from the bulky, unreliable vacuum tubes and transistors of the past. The massive investment and demand from the Apollo program drove down their cost and spurred their rapid development, creating the foundation for the entire modern computer industry. The smartphone in your pocket, the laptop on your desk, and the global network that connects them all owe a direct debt to the engineering needs of landing on the moon. Apollo was a catalyst that compressed decades of technological progress into a few short years, spinning off innovations in materials science, medicine, and telecommunications that we still benefit from today. Ultimately, the greatest legacy of those 6 lunar landings may be the inspiration they planted in the human spirit. For a generation of children watching grainy black and white broadcasts, the moon was no longer a distant myth, it was a destination. It made science and engineering seem like the most exciting adventure imaginable, fueling a surge in students pursuing those fields. The Apollo program demonstrated that with vision, resources, and relentless determination, humanity could achieve the seemingly impossible. It was a testament to what we can accomplish when we look beyond our terrestrial squabbles and reach for the stars, a lesson in potential that continues to echo through every new mission we send into the deep. While humanity was reaching for the moon, 2 radio astronomers in New Jersey were trying to eliminate a persistent and deeply annoying noise. Arno Penzias and Robert Wilson were not cosmologists. They were engineers at Bell Labs using a massive, ultra-sensitive horn antenna built for satellite communications. Their goal was simple: measure the faint radio waves from our own galaxy. But a mysterious, constant hiss plagued their instrument, a static that came from every direction in the sky, day and night, and would not go away. They checked everything. They pointed the antenna at New York City, thinking it was urban interference. They scrubbed the entire instrument, even famously evicting a pair of pigeons that had nested inside and carefully scraping away their conductive white droppings, which they jokingly referred to as a dielectric material. The noise remained. It was as if the universe itself was humming a single, quiet note. This was not a problem with their equipment, it was a signal from the dawn of time. At the same time, just 30 miles away at Princeton University, a team of physicists led by Robert Dick was actively searching for this exact phenomenon. They were working on a theory that the universe began in a hot, dense state, a colossal explosion. If that were true, they reasoned, the entire cosmos should be filled with a faint, cool remnant of that initial fireball, a cosmic afterglow that had been stretched by the expansion of the universe over billions of years into the microwave part of the spectrum. When Penzias and Wilson, frustrated, called Dick for advice, the Princeton team immediately understood what they had found. The two groups published papers together in 1965. Penzias and Wilson described the puzzling signal, and Dick's team interpreted it as the echo of creation. That faint, omnipresent hiss was the cosmic microwave background radiation, the cooled and redshifted light from the moment the universe became transparent, just 380,000 years after the Big Bang. It was the oldest light we can ever see, a baby picture of the cosmos. This discovery was the final, irrefutable piece of evidence that swung the scientific consensus decisively in favor of the Big Bang theory over its rival, the steady-state model. It proved the universe had a definite beginning, a moment of birth, and it gave cosmologists a fundamental measuring stick. Tiny, microscopic fluctuations in the temperature of this background radiation, which we can now map with incredible precision, are the seeds of all cosmic structure. Those faint ripples are the gravitational blueprints for everything that would eventually form. The first overdensities that, over eons, collapsed under their own gravity to create the vast cosmic web of galaxies, stars, and planets we see today. Penzias and Wilson had set out to clean a radio antenna and instead found the fossilized echo of the universe's first breath, an accidental discovery that earned them a Nobel Prize and forever anchored our origin story in observable reality. That faint background hum of creation was a silent movie of the universe's infancy, but a new discovery would soon give the cosmos a voice. For a century, Einstein's theory of general relativity had predicted that cataclysmic events should send ripples through the very fabric of spacetime itself. These were gravitational waves, distortions that would travel at the speed of light, stretching and squeezing everything in their path by an almost infinitesimal amount. The challenge was detecting them. The distortion from even the most violent events in the universe would be smaller than the width of a proton over a distance of 2.5 miles. It seemed an impossible task. Then, on September 14, 2015, the twin detectors of the Laser Interferometer Gravitational Wave Observatory, or LIGO, registered something extraordinary. After traveling for 1.3 billion years, a ripple in spacetime passed through the Earth. For just 0.2 of a second, the laser beams in the two facilities, separated by nearly 2,000 miles, were jostled in perfect, undeniable synchrony. The signal was a cosmic drumbeat that started at a low frequency and then rapidly rose in both pitch and strength, ending in a final, characteristic chirp. This was the sound of two black holes, each about 30 times the mass of our Sun, caught in a final, fatal dance. They had spiraled around each other for eons, and in the last frantic moments before they merged, they whipped spacetime itself into a frenzy, releasing in a fraction of a second more power than all the stars in the observable universe combined. The resulting single, more massive black hole was ringing like a bell, its final vibrations imprinted on the fabric of reality. This detection was not just a confirmation of Einstein's genius. It was the opening of an entirely new sense for humanity. For all of history, we have explored the universe by collecting light, from the visible rays our eyes can see to the radio waves and X-rays our telescopes can detect. But gravitational waves are fundamentally different. They are not light. They are a direct disturbance of the stage upon which everything plays out. This means we can now hear events that are completely dark to traditional astronomy. We can listen to the invisible collisions of black holes, the mergers of neutron stars, and the rumblings from the very first moments after the Big Bang. It is as if we have been watching a silent film of the universe for centuries and have suddenly been given headphones, allowing us to hear the soundtrack of cosmic violence and creation for the very first time. That new sense of hearing the cosmos was soon joined by a sense of touch, as something tangible from another star system brushed past our own. In October 2017, a University of Hawaii astronomer named Robert Wurick was reviewing data from the Pan-STARRS telescope when he spotted an object moving at staggering speed. It was not orbiting the Sun, it was passing through, a cosmic bullet fired from the depths of interstellar space. They named it Oumuamua, a Hawaiian word meaning scout from the distant past. This was the first confirmed visitor from another star, a moment of profound historical significance. Its trajectory was the first clue to its alien origin, a hyperbolic path that meant it was just passing through, never to return. But its physical characteristics were even more bizarre. As it tumbled through our solar system, measurements of its changing brightness revealed an extreme, unprecedented shape. Oumuamua was not round, it was not even lumpy. It appeared to be highly elongated, perhaps 10 times as long as it was wide, resembling a cosmic cigar or a pancake. Nothing like it had ever been seen before. The strangeness did not end there. As it sped away from the Sun, something unexpected happened. It accelerated slightly, as if being pushed. A comet would do this as the Sun's heat vaporizes its ice, creating a jet of gas that acts like a tiny engine. But Oumuamua showed no visible coma, no tail of gas and dust that all comets display. It was a dark, silent, and seemingly barren rock, yet it was accelerating as if it had a secret of its own. This single anomaly sparked a firestorm of scientific debate. Most scientists proposed natural explanations. Perhaps it was a shard of a planet shattered by a distant cosmic collision, tumbling through the galaxy. Maybe it was a very old comet whose outer layers had been baked by eons of cosmic radiation into a thick, carbon-rich crust that trapped its volatile ices inside. When heated by the Sun, those subsurface ices could have vented through hidden pores, providing the thrust for its acceleration without producing a visible tail. But the mystery was so compelling that a few scientists, like Harvard's Avi Loeb, raised a more speculative possibility. Could Oumuamua be artificial, a piece of advanced alien technology, perhaps a light sail using the pressure of sunlight for propulsion? While this was considered a remote possibility by most of the scientific community, the very fact that the question could be seriously discussed marked a shift in our thinking. Regardless of its true nature, Oumuamua delivered one undeniable, transformative truth. It proved that our solar system is not an isolated island. We are constantly being visited by material from other stars, pieces of distant worlds and other suns. These messengers are likely passing through all the time, too small and dark to see until our telescopes became powerful enough to catch them. Oumuamua was the first scout we noticed, a silent, tumbling monument to the fact that the galaxy is a dynamic, interconnected place, and that we are now, for the first time, capable of meeting our interstellar neighbors. 23 years ago, the abstract threat from space became terrifyingly real. On a clear winter morning in February, the people of Chelyabinsk, Russia, were starting their day when the sky suddenly erupted in a light brighter than the Sun. A 65-foot-wide asteroid, undetected by any telescope, had slammed into the Earth's atmosphere at 40,000 miles per hour. It was not a small shooting star. This was a 20,000-ton rock exploding with the force of 500 kilotons of TNT, over 30 times the energy of the Hiroshima bomb, in a massive airburst 12 miles above the city. The event unfolded in a sequence of pure, visceral terror captured on countless car dashcams and security cameras. First came the blinding fireball, a blazing trail of superheated rock and air streaking across the blue sky. Then, minutes later, the shockwave arrived. It was a wall of sound and force that shattered windows for hundreds of miles, sending glass flying into homes, schools, and offices. Over 1,000 people were injured, not by falling rock, but by the indirect effects of the blast wave. The sheer power of the event registered on infrasound sensors across the globe, a seismic signature of a cosmic blow. Chelyabinsk was a cosmic wake-up call delivered directly to a populated area. It demonstrated with brutal clarity that an asteroid does not need to be a planet killer to cause massive damage and human suffering. The object that exploded over Russia was a relatively small one, the kind that statistically hits Earth every few decades. The real shock was that it arrived completely without warning, sneaking up on us from the direction of the sun, where our telescopes are blind. This single event, witnessed by millions online through viral video, transformed planetary defense from a theoretical exercise into an urgent global priority. In its aftermath, funding and international cooperation for asteroid detection programs surged. NASA Planetary Defense Coordination Office was established, and new, more powerful telescopes were commissioned with the specific goal of finding these smaller, yet still devastating, near-Earth objects. The lesson from Chelyabinsk was simple and stark. Our civilization exists under an occasional but inevitable cosmic bombardment, and if we do not find them first, the next one will not just be a spectacular light show. It will be a disaster. The invisible force of a black hole had finally been rendered visible. For the first time in human history, we were not just listening to the gravitational echoes of these cosmic monsters, but staring directly into the abyss. On April 10, 2019, a global team of scientists unveiled an image that seemed to defy reality itself. It was a fiery, asymmetrical ring of light, a brilliant orange halo encircling a perfect circle of shadow, the supermassive black hole at the heart of the distant galaxy Messier 87. This was not an artist's impression. It was a direct, empirical photograph of the event horizon, the point of no return where gravity becomes so intense that not even light can escape. To capture this image of an object 55 million light-years away, astronomers had to create a telescope as large as the Earth itself. They synchronized a global network of 8 radio observatories, from the high deserts of Chile to the volcanic peaks of Hawaii and the frozen plains of the South Pole. This collective instrument, known as the Event Horizon Telescope, functioned as a single planet-sized eye. The data they collected was so vast it could not be sent over the internet. The hard drives, filled with petabytes of information, had to be physically flown to central processing centers where supercomputers correlated the signals. It took 2 years of meticulous analysis to assemble the final picture from this cosmic jigsaw puzzle. The image we saw was not the black hole itself, which is by definition unseeable, but its shadow silhouetted against the incandescent whirlpool of its accretion disk. The superheated gas, spiraling inward at near light speed, glowed with intense radiation, tracing the violent geometry of spacetime itself. The bright, lopsided ring confirmed a key prediction of Einstein's general relativity, the phenomenon of gravitational lensing. The black hole's immense gravity was acting like a lens, bending the light from the far side of the accretion disk around itself and magnifying it, creating that iconic, uneven circle of fire. This single, hazy image transformed black holes from theoretical phantoms into tangible, observable objects. It confirmed that these gravitational giants not only exist but govern the dynamics of entire galaxies, from the stars orbiting their centers to the very shape of the cosmos. We had finally turned a cosmic myth into a photograph, proving that even the darkest secrets of the universe cannot hide forever from the collective curiosity of humanity. That new ability to see the cosmos, once the sole domain of governments, is now being opened to everyone. The 22nd cosmic event is not a distant supernova or a rogue asteroid, but a revolution happening in our own atmosphere, driven by private companies like SpaceX and Blue Origin. For decades, spaceflight was an incredibly expensive endeavor reserved for superpowers, where rockets were used once and then discarded into the ocean. This all changed with a single, breathtaking sight: the vertical landing of a rocket booster. The development of reusable rockets is not just an engineering improvement, it is a complete paradigm shift. By landing and reflying these massive boosters, companies have slashed the cost of reaching orbit by a staggering margin. Think of it like the difference between building a new airliner for every single flight versus using the same plane repeatedly. This newfound affordability has unleashed a flood of innovation and access. Small companies can now launch satellites, universities can send up experiments, and even private citizens can buy a ticket to orbit. This democratization of space is the first step in weaving it into the very fabric of our economy and daily lives. One of the most visible results is the rapid deployment of mega-constellations, vast networks of thousands of small satellites like SpaceX's Starlink. From the ground, we see them as strings of lights marching across the night sky, but their purpose is to blanket the entire planet with high-speed internet. This promises to connect remote communities, ships at sea, and aid workers in disaster zones, effectively erasing the digital divide from orbit. Yet this ambition comes with a cosmic cost, raising urgent questions about the long-term sustainability of our orbital environment. The most profound impact of this private space race, however, is its tangible progress toward a goal that was once pure science fiction, making humanity a multi-planetary species. The development of massive new spacecraft like SpaceX's Starship, designed not just for orbit but for journeys to the Moon and Mars, represents the most concrete plan for human expansion ever conceived. These are not paper concepts, they are steel cylinders being built and tested, sometimes explosively, in real time. This is no longer a distant dream for our grandchildren. It is a project with a timeline, aiming to establish the first permanent, self-sustaining cities on another world within our lifetime. This changes our relationship with the cosmos on a fundamental level. We are no longer just visitors or observers looking up at the stars. We are becoming gardeners, preparing to plant the seeds of human civilization in the sterile soil of Mars. We are becoming miners, looking to asteroids for the rare minerals that will build our future in space. We are becoming a spacefaring civilization, taking our first deliberate steps to ensure that the story of humanity does not have all its eggs in one planetary basket. The rise of private spaceflight is the cosmic event that is actively building the launchpad for our future among the stars. That new launchpad for our future depends on a deeper understanding of our cosmic past, and in July of 2022, a new eye in the sky gave us our clearest view yet. The first full-color images from the James Webb Space Telescope were not just pictures, they were portals. One of the very first, a stunning deep field, revealed a patch of sky no larger than a grain of sand held at arm's length, yet it was filled with thousands of galaxies, each a swirling island of billions of stars. This was not a new sky, it was an ancient one. The light from some of those faint red smudges had been traveling for over 13.5 billion years, showing us what the universe looked like when it was a cosmic toddler, a mere 300 million years after the Big Bang. Webb's infrared eyes are a time machine, allowing it to see through cosmic dust and catch the stretched, reddened light from the first stars and galaxies to ever ignite. And what it found there was a revolution. These infant galaxies were not the small, chaotic blobs we expected. They were massive, mature, and structured, with fully formed disks and spiral arms far earlier in cosmic history than any theory had predicted. It was like opening a history book to the first chapter and finding a sophisticated civilization already in place, forcing us to rewrite our models of how the universe built its largest structures. But Webb's gaze is not only fixed on the distant past, it is also turning its powerful mirrors toward our galactic neighborhood, to the atmospheres of planets orbiting other stars. By watching as an exoplanet passes in front of its host star, Webb can analyze the starlight filtering through that world's air. It looks for the chemical fingerprints of specific molecules, a technique called spectroscopy. And it has already delivered breathtaking results, detecting water vapor, methane, and even carbon dioxide in the skies of alien worlds. For the first time, we are not just guessing what these planets are like, we are taking a direct chemical census of their air. This is the foundational work for the ultimate discovery. One day, perhaps soon, that spectrum from a rocky, Earth-sized world will show a telltale imbalance. a mix of gases that should not exist together without a constant, renewing source. Something like oxygen and methane, a combination that on our planet is a clear signature of life. The James Webb Space Telescope is more than an observatory, it is a promise. It is the instrument that may finally turn the philosophical question of whether we are alone into an empirical one, giving us the first hard data point in humanity's greatest mystery. The search for a voice in the cosmic static is one of humanity's most profound and enduring quests. It began in earnest in 1960 when a young astronomer named Frank Drake pointed a radio telescope in West Virginia toward two nearby, sun-like stars called Tau Ceti and Epsilon Eridani. His project, named OSMA, was the first scientific attempt to listen for deliberate signals from an alien civilization. For 150 hours he scanned the stars, hearing nothing but the natural hiss of the universe. Yet that simple act transformed a philosophical question into an experimental one, launching the modern search for extraterrestrial intelligence, or SETI. The core logic is breathtakingly simple. For over a century, our own civilization has been leaking radio and television signals into space, a growing bubble of transmissions that now extends over 100 light-years in every direction. If another technological society exists, it might be doing the same, either deliberately beaming a hello across the void or simply leaking its own electronic chatter. The challenge is not the listening, but the sheer, staggering scale of the cosmic ocean we must search. The radio spectrum is vast, and a signal could be coming from any one of the hundreds of billions of stars in our galaxy on any frequency, and it might only be transmitting for a brief window of time. It is like trying to find a single, specific grain of sand on every beach on Earth without knowing which beach to look on. This monumental task has been supercharged in the 21st century by initiatives like the Breakthrough Listen project. Instead of focusing on a few stars, it uses some of the world's most powerful telescopes, like the Green Bank Telescope in West Virginia and the Parkes Observatory in Australia, to conduct a galactic census, scanning millions of nearby stars, the entire galactic plane, and even over 100 nearby galaxies. The amount of data collected is almost unimaginable, requiring advanced algorithms and artificial intelligence to sift through the noise, searching for that one unnatural needle in a cosmic haystack. The discovery of even a simple, repeating signal, a prime number sequence or a pulse of pure mathematics, would be instantly recognizable as artificial. It would tell us one thing with absolute certainty: we are not the universe's only children. The implications would ripple through every facet of human society, from science and philosophy to religion and art. It would force us to see ourselves not as the pinnacle of creation, but as a single thread in a vast cosmic tapestry of life and intelligence. The search itself, this act of reaching out with our technology and our imagination, is a cosmic event of a different kind. It is not something that happened to us, but something we are actively doing to ourselves, pushing our science to its limits and preparing our minds for a revelation that would forever change the story of humanity. What new chapter would we write if we finally knew we had neighbors? Our relentless search for a cosmic neighbor is driven by a fundamental truth that our own home star holds a final, inescapable destiny for this world. Billions of years from now, the steady fusion reactor at the center of our solar system will begin to falter. Having spent its life burning hydrogen into helium, the sun will start to exhaust its core fuel. In response, its core will contract, growing hotter, while its outer layers will swell dramatically, bloating outward to engulf the orbits of Mercury and Venus. Our sun will transform into a red giant, a monstrous, dying star that will fill the Earth's sky. The oceans will boil away into steam, the mountains will melt into rivers of lava, and the very rock of the planet will be vaporized, consumed by the stellar inferno. The Earth, the only home humanity has ever known, will cease to exist, return to the elemental stardust from which it was formed. This is not a speculative disaster or a potential threat. It is a guaranteed event written into the laws of physics, a cosmic countdown clock that has been ticking since the moment our world was born. This ultimate cosmic event forces a profound perspective on our place in the universe. All the empires, all the art, all the love and loss and triumph that has ever happened on this planet, every single human story, resides on a temporary world. This realization is not a cause for despair, but the greatest possible motivation. It makes the expansion of humanity beyond Earth not a luxury or an adventure, but a fundamental necessity for the long-term survival of our species, our culture, and our collective memory. The story of life does not have to end with the death of our star. The same curiosity that led us to decode the whispers of gravitational waves and photograph the shadow of a black hole is the very tool that can secure our future. We are the first life forms on this planet with the ability to comprehend our own end and the technological potential to avoid it. This transforms our journey into space from a mere exploration into a migration, a biological and cultural imperative to plant the seeds of humanity on other worlds around other stars. The silent, expanding death of our sun is the final and most powerful argument for why we must look upward, why we must build, and why we must sail onward into the great cosmic ocean, ensuring that the echoes of humanity are heard long after our cradle has turned to ash. Each cosmic event we have witnessed is not a solitary note, but a single thread in an intricate tapestry. The supernova that died to forge the iron in our blood is the same cataclysm that seeded the cloud which birthed our sun. That solar system's formation, in turn, was punctuated by the asteroid impacts that delivered the water for our oceans and the organic compounds for our cells. These are not separate stories, they are one continuous chain of causality, a grand cosmic narrative where every ending is a new beginning. The oxygen we breathe was a poison excreted by ancient cyanobacteria, a biological revolution made possible by a stable climate gifted by our moon, which itself was born from a planetary collision of unimaginable violence. Every time you take a breath, you are participating in a sequence of events that spans the lifetime of the universe. This interconnectedness reveals a profound truth about our place in the cosmos. We are not merely inhabitants of a random planet. We are the universe becoming conscious of itself. The same physical laws that govern the spin of a galaxy and the explosion of a star also govern the electrical impulses in our brains, allowing us to develop the curiosity and intelligence to trace our own origins back to those very events. We are the universe looking back at its own history, reading its autobiography in the light of distant stars and the silent whispers of gravitational waves. How many other chains of cosmic coincidence are unfolding right now, on worlds orbiting distant suns, leading to other forms of consciousness looking up at their own skies and wondering if they are alone? Our story is a single, beautiful example of what the cosmos can create when given enough time and the right star-crossed ingredients. This long chain of cosmic causality, from stellar ash to conscious life, is our true inheritance. Our entire history, every triumph and tragedy, was written into the stars long before we existed to read it. We began with a violent collision that gave us a stable world, were shaped by stellar explosions that forged our very atoms, and were granted opportunity by the very impacts that threatened to destroy us. Now we stand at a pivotal moment in this grand narrative, armed with the knowledge of our own celestial origins and the foresight of our star's eventual demise. We are the first generation to hold the entire story in our hands, from the birth of the moon to the future death of the sun, and with that knowledge comes a profound responsibility. This is not the end of the story, but the beginning of a new chapter, one that we must write ourselves. The next great cosmic event will not just happen to us, it will be shaped by us. It is the story of our migration from a single planet to a multi-planetary species, of our search for other minds in the darkness, and of our ultimate survival beyond the life of our star. So the next time you find yourself under a clear night sky, look up, See not just points of light, but see the supernova forges, the planetary construction sites, and the potential homes for our distant descendants. Let that view fill you with a sense of connection, not isolation. Support the quest for knowledge, for every new telescope and every daring space mission is an investment in our cosmic future. We are the universe awakening to its own story. Our greatest task now is to ensure that story continues, to carry the legacy of stardust forward, and to become a lasting voice in the infinite, whispering cosmos.